Okay, well, welcome. We'll just wait probably 30 seconds more just to wait for anyone who is dialing in slightly late. So just bear with us for a few minutes more. Okay, well, impatience is one of my overplayed strengths. So welcome everyone to the second of our series of 5G webinars. How will 5G power AI and Industry 4.0? For those of you who don't know me, my name is Paul Graham. I head up the Telecoms sector group at Fieldfisher. Delighted to be joined today by Chris Eastham, who's the director in the Telecoms sector group and specialises in the law relating to AI and emerging technologies.
Hi, everyone.
And as I said, during today's session, we're going to discuss how 5G will impact developing use cases for AI and Industry 4.0. So if we can go to the agenda slide, in terms of the agenda, we're actually going to start off in a slightly odd place, which is looking at some of the negative press associated with 5G business investment cases, look at the likely timeline for the introduction of new functionality in 5G networks and how this may affect operators' business models. Chris will then do the bulk of the talk, looking at how 5G networks and AI can work in tandem and how network slicing functionality can open up new business opportunities. I'll then conclude by looking at some of the security challenges posed by 5G and what the associated security regulatory landscape will look like. So on to the next slide. Yeah, we set out a diagram here that many of you will be familiar with. It's the ITU's 5G services hierarchy. So just by way of recap, the first domain at the top of the triangle, traditional enhanced mobile broadband domain, and the other two domains are entirely new. So massive machine type communication. So in other words, the ability to have lots of communicating devices in one place, and ultra reliable low latency communications. And this low latency feature is probably the most influential factor in the 5G services hierarchy. To deliver services over a wide area network with a consistent round trip of 5 milliseconds or less is going to be extremely challenging. It will require a new system architecture, and physical assets will need to be located much closer to the edge of the network in order to deliver that level of latency. So if we can go to the industry criticism of the 5G investment case slide. Yeah, so I guess in summary, 5G potentially offers the industry a new way to deliver data and services to businesses and consumers. And you could say this is a massive opportunity for the telecom sector, given the sheer amount of data required by new technologies such as the Internet of Things, AI, and machine learning. And these technologies deployed to enable huge numbers of different use cases ought to vastly increase the flow of traffic over telecoms networks. So given this huge potential, it's slightly surprising to see some mixed press about the merits of 5G investment. So in William Webb's book, which is on the left-hand side of the slide, he provides a critique of the need for investment in 5G, saying that it's overhyped, the investment case is unproven, and that many use cases just won't need 5G, and actually constant connectivity as opposed to the gigabit speeds promised by 5G might be a better model in terms of deployment. And this critique has also occasionally been backed up by operators' public statements about investment in 5G. And you can see both Vodafone and Three have questioned that. And it's worth sort of, if we can stay on that slide for a while, it's worth just, in terms of the impact on networks, these are likely to need to support billions of application-heavy video streaming, mobile devices, and emerging IoT applications. all of which are going to require on-demand scaling, high resiliency, and the ability to change services in real time. And as exciting as these opportunities appear now, it is possible that the road to implementation of 5G will be quite long. And that's partly because the capital investment needed to fulfill 5G's promise is huge. So whilst 4G LTE relies upon relatively few masts that are built miles apart, 5G will require lots of small cells much closer together. And these mini 5G base stations may be placed on top of streetlights or on the sides of buildings every few hundred feet in urban areas. And basically, building these sorts of networks is going to take time, and it's going to be expensive. As we'll show on this release 15 and 16 slide that we've got, networks are likely to change in an iterative way. So the tricky financial considerations and the evolutionary nature of 5G technology means that we think the rollout of 5G is likely to come in a number of waves. And that's reflected by the work of the 3GPP standards body in developing emerging technical standards for 5G. So if you look at the first, if you like, stable release of 5G functionality was release 15. It ended up being split different phases with the finalized version being released in the last quarter of 2019. And what happens is 5G is stated to be released over 3 different releases, 15, 16, and 17, and they tend to overlap in terms of time frame, so they're non-sequential. So as one release, such as release 15, is finalized, you've already got the framework for release 16 and release 17 also having been approved. If we can then go on to release 16 and 17 timescales. So the timelines on this slide, which sets out release 16 and 17, have actually slipped somewhat due to COVID. So release 16 is now due to be frozen over the next month or so. It was originally due to be completed in the end of the first quarter. And there'll be a similar delay in terms of release 17. So what we'll do over the coming slides is just explain what the stable functionality of release 15 is and what we can expect to see in release 16 and 17 as those are released to the market. So if you can go on to the release 15 slide. So release 15, which was finalized the back end of last year, basically it brings a sort of huge technology step with the creation of what's called 5G New Radio. And that will evolve across releases 15 to 17. For 5G, many operators are starting with dual connectivity between 4G LTE and 5G New Radio equipment, effectively using what's called a non-standalone release. So release 15 contains the bulk of the building blocks for the establishment of 5G networks and associated services such as autonomous vehicles, IoT, and smart cities. And Chris will go into more depth about these use cases later in the webinar. The 2 key concepts on the slide that I wanted to introduce to you before I hand over to Chris, basically 5G networks such as service-based architecture and 5G New Radio and network slicing. So over the next 2 slides, I'll give a brief outline of 5G New Radio and network slicing, and then Chris will discuss these concepts and their business applications in a bit more depth. Great. So as I mentioned earlier, to truly implement the full version of 5G New Radio, a massive investment is going to be required by operators in new hardware. So in order to continue using existing hardware, a phased approach has been taken. And so there is, in its simplest terms, 2 different deployment options for 5G. The The first one being non-standalone, that uses 4G LTE core network, and then a standalone version which will use 5G core network that's completely independent of the existing 4G network. So in the non-standalone architecture, the 5G radio access is used in conjunction with the 4G core, and that basically delays the need for whole-scale network replacement. It's sort of important to understand in terms of sort of looking beyond some of the hype around 5G, that under these sorts of deployments, really predominantly 4G services are supported, but they will enjoy some of the capacities offered by 5G RAN, such as lower latency. And the non-standalone architecture is seen as a temporary measure towards a full 5G deployment. And basically in this mode, 5G new radio base stations effectively connect to 4G LTE base stations via what's called an X2 interface. Moving on then, in terms of the standalone option, 5G new radio is connected to the 5G core network, and it's only really in this configuration that the full set of 5G phase 1 services are supported. And this is basically seen as being a full 5G deployment that doesn't need any part of the 4G network to operate. And these standalone deployments rely on what's called the so-called service-based architecture, where the network architecture elements are defined in terms of network functions rather than by traditional network entities. And on this next slide, I'll sort of talk briefly about those. So in order to support the different services that we'll come on to discuss later, 5G uses basically a service hosting environment, which is a service platform located inside the operator's network. And this service platform offers hosted services closer to the end user to meet specific requirements like low latency, and also to reduce the load of traffic on the transmission network. And to enable the network to do this, the 5G core network selects a user plane function close to the end user device and basically executes traffic steering to that user plane function via an interface. And this will enable support of ultra reliable low latency communications and support for different session and service continuity modes. And then just a brief introduction to network slicing. A network slice is essentially a set of network elements specialized in the provisioning of a certain type of service. So for example, an operator can implement one network slice for Internet of Things, another one for supporting classic end user devices and mobile broadband, and another one, for example, for vehicle to anything communication. And also within those network slices, there can be different requirements in terms of functionality, so policy control and priority of traffic processing, differences in performance requirements, so latency, mobility, and data rates, or actually a network slice can serve only a specific type of user. So for example, a public safety user, a corporate customer, a roaming customer, or hosting of an MVNO's traffic. And all of these different slices can be used simultaneously. And I think one of the things to bear in mind is that actually automating the setup and management of those network slices, including configuring the underlying IP network, is likely to be critical to operators' business case for 5G investment. So based on an operator's particular business scenarios, they can decide how many network slices to deploy and what functions and features to share across multiple slices. And the characteristics of each slice are defined in terms of quality of service, bit rate, and latency. And in terms of the release 15, there are 3 types of predefined slices within 3G PP standards. So type 1 is dedicated to the support of enhanced mobile broadband. Type 2 is for ultra reliable low latency comms, and type 3 is essentially for the mobile Internet of Things. And this sort of standardization should allow for reduced coordination efforts between operators. And obviously operators are free to configure their own network slices, but the base functionality has been sort of locked down in terms of release 15. And then go to, so release 16, which is due to be finalized in the next few months. The most notable enhancements are in the areas of MIMO, beamforming enhancements, dynamic spectrum sharing, carrier aggregation, and user equipment power saving. Slide, which is pretty busy. What we've covered here is, and this is going to be hugely important for particular use cases, is just the improvements in terms of cell positioning that are implemented by release 16 and release 17. So normally positioning has been accomplished with global navigation systems assisted by, so satellites in other words, assisted by cellular networks. And this existing approach gives you accurate positioning, but is typically limited to outdoor areas with satellite visibility. And there's a whole range of new applications that require accurate positioning, but not only outdoors, but also indoors. And in essence, release 16, by using time of arrival type processing and the positioning reference signals in release 15, will really enable networks to provide very accurate positioning, both outdoors and indoors. And that will really, I think, release a whole bunch of new business use cases that currently are not really ready for market. So in terms of what we think this will mean in terms of the business models for operators, if we can go to the next slide, we think arguably there'll be a potential move away from a model whereby operators sell connectivity to businesses who then use digital services from OTT players. And so you may see what we see as a business to business to X model, where either an operator bundles third-party products such as virtual reality gaming within their data plans, and those include a VR content subscription at package rates, or actually a third-party cloud provider or video streaming service includes a 5G connectivity as part of its own offering, whilst paying the operator for network usage. And I think that how operators sort of capitalize on that will be key, I think, to the success of 5G and how likely those business investment cases are to come to market. So I'll now hand over to Chris to talk about network slicing and the like in a bit more detail.
Thanks very much, Paul. So before I begin looking at the impact that 5G is going to have, I think it's worth saying that there's a lot of hype around all the use cases that it's going to enable. And Paul's touched on this. Whilst it's no doubt true that it will have a big impact, it may be that some of those use cases are going to be better served by other technologies. That said, I will try not to let that dampen my enthusiasm too much when we're exploring the possibilities today. So first of all, 5G, AI, smart platforms, and IoT form the basis of what some are calling intelligent connectivity. And this marks the beginning of an era of highly contextualized and personalized experiences, which are underpinned by ubiquitous hyperconnectivity. It's going to impact almost every aspect of our daily lives, from the way we consume entertainment to the way in which we work and interact with colleagues. It'll give us the information that we need when we need it, making our lives more productive and more efficient. And it's going to change how entire industries innovate and operate, how societies interact and thrive, and how economies flourish. So mobile connectivity is already helping buildings and cities to become smarter, safer, and more sustainable. The rollout of 5G is going to accelerate this trend by enabling the deployment of large numbers of connected sensors and actuators. And that will give municipalities, organizations, and individual citizens the ability to monitor and control what's happening in and around their properties. If every road user can communicate with everything else in the vicinity, then road transport is going to be much safer and more efficient. Vehicles, bicycles, pedestrians could relay their position to other road users in real time, enabling AI systems to use intelligent connectivity to instruct vehicles when to slow down and when to accelerate. This could remove the need for traffic lights and speed cameras and similar devices. Even before self-driving cars become mainstream, 5G could make a major difference to the motoring experience by relaying pertinent information from roadside infrastructure and from other nearby vehicles. Intelligent connectivity could also enable us to work more flexibly, adapting to the changing needs of business. You could, for example, move everything into the cloud to achieve greater agility. You could flex your buildings, renting them in smaller units by the desk rather than by the floor. And with the wireless office, you don't have to change your infrastructure when you reconfigure your floor plan. You'd have the ability to deploy and redeploy working spaces in a much more flexible way. I'll talk about industrial IoT in just a second. Artificial intelligence systems are developing to a point now where they can understand and employ natural language to interact with humans. And as a result, people will be able to query or instruct a personal assistant hosted in the cloud, regardless of where they are. Individuals might wear a 5G headset or similar, allowing them to converse with the personal assistant, which will be able to respond in milliseconds to requests for information, while simultaneously handling related transactions in the background. So, for example, a business traveler or tourist could ask a personal assistant to find and book tables in restaurants, to book train tickets, check train times, and to organize hotel rooms. The assistant would require minimal instructions because, of course, it's already aware of the individual's preferences and even learns as it goes. And then in wellness, as 5G networks are able to support such large numbers of connections simultaneously, people will be able to wear connected wellness and security monitors. And these can provide continuous information about heart rates, blood pressure, temperature, stress levels, and location, and also enabling emergency alerts in the event of a fall or an attack. Now, all this information will help individuals to monitor their personal condition, as well as take advantage of enhanced health insurance programs, predictive healthcare, and personal security solutions. Now, all this is something of a grand vision of the future, but I think we can start to examine how these emerging technologies could work together to bring it into reality. So first of all, let's have a look at how 5G could enable AI in general terms. So 5G is set to deliver huge bandwidth, millisecond latencies, and reliable connections. And this allows us to shift computing between devices and the cloud to optimize how networks and computing resources are used. And of course, that supports AI processing. Because 5G gives better, faster access to the services operating in the cloud, it brings information, computing power, and the user closer together. So the impact of this is that the service feels more local to the user, whilst at the same time, the AI is able to access and process the user's data faster. 5G can support up to 1 million concurrent edge devices per square kilometre, which is orders of magnitude greater than with 4G technology. And that last mile scale will enable businesses to collect vast amounts of data continuously from 5G equipped devices in an emerging paradigm which we know as multi-access edge computing, also known as wireless edge computing. And as 5G networks begin to flood data streams everywhere with fresh data from all these devices, it'll enable AI data lakes to be replenished in real time, enabling more sophisticated analytics and machine learning models for real-time applications. 5G's low latency, together with AI's decision-making capabilities, are going to be combined to enable smart devices to respond in real time to a changing operating environment. Now, as I said, it enables wireless edge computing, which is all about shifting intelligence from the central cloud to a complementary combination of the edge cloud, which is in the middle, and edge on-device intelligence, which is on the right. And this diagram represents the movement of compute resources to the services that interact directly with the edge devices, whether in the cloud or putting the intelligence on the edge device itself. And I've also set out some examples of edge devices, which could be those found in the home at the top, which could be personal devices, gaming rigs, domestic smart devices, those found in industry, including secure access devices, sensors, and industrial automation, and those that we those that we use when we're on the move, such as wearables, mobile devices, and vehicle control systems and infotainment. But what's the advantage of wireless edge computing? Well, by putting computing power on the device itself, we can enhance security as well as privacy compliance because it keeps the data local. It also allows customization and personalization of the applications and gives the user autonomy. It gives immediacy by operating tasks at the device level, and it makes efficient use of bandwidth and spectrum, which are of course finite resources. On-device processing is complemented by processing at the edge of the cloud. That augments on-device capability with scalable processing power, enabling service providers to deliver added value services. Of course, it relies on low latency and may require ultra-reliable low latency communications, which Paul's mentioned and I'll talk about shortly in the context of Industrial IoT. But what about the other way around? How is AI going to support 5G? Well, the main way that I see it supporting 5G is likely to be AI ops, and that's embedding intelligence into network operations. Firstly, we know that there's going to have to be a lot of investment to make 5G work. Purchasing spectrum comes at a significant cost to service providers, and then on top of that, key investments in core and radio access networks, as well as hardware updates, are going to be needed to account for the greater cell density and tower infrastructure that's required for 5G to function. AI can help here by keeping running costs down in order to soften the blow. AI could enable the end-to-end automation of processes in a scalable way, and so could be used to reduce overall running costs resulting from process inefficiencies. To serve the next generation of distributed AI applications effectively, 5G networks are going to have to become continuously self-healing, self-managing, self-securing, self-repairing, and self-optimizing. Basically, they need to look after themselves. This, in turn, relies on AI ops to take control of application-level traffic routing, quality of service assurance, performance management, root cause analysis, and other operational tasks. And it's going to have to do this more scalably and more efficiently than manual methods alone. AI ops is going to drive differentiated quality of service across 5G environments in conjunction with network slicing, which I'll talk about in a moment. AI-based controls will ensure that radio frequency channels and other infrastructure resources are provisioned dynamically to support changing quality of service requirements, changing traffic patterns, and application workloads. And they will also support continuous configuration and reconfiguration and proactive subscriber experience optimization. Now, I've mentioned resource allocation, and that includes 5G's dynamic radio frequency channel allocation. As a rule, 5G uses smaller cells than 4G. It reuses frequencies more intensively and must continuously retarget the antenna for each edge device. And that's because it uses beamformed phase array millimeter wave antenna to communicate with the edge device. So to ensure quality of service, 5G base stations dynamically predict and provision the best wireless path to each device. Because of the high frequency spectrum that's being used, signals are readily attenuated by walls and other solid objects which might get in the way. And so the base stations need to account for this in provisioning optimal network paths. This needs real-time analytics to perform the necessary calculations. And it then makes the constant changes necessary to provide the most efficient local loops. So how can communication service providers facilitate this? So in order to make the most of these opportunities, CSPs need to take a proactive approach. And this could include building standardized interfaces to enable AI access to relevant and actionable data, exploring ways of using AI to optimize the customer experience, running early trials to identify ways of using AI to deliver new services, examining the use of AI and automation for network operations, including planning and network optimization, and just being early adopters of new solutions using AI and automation to facilitate the development of new use cases. So we've mentioned network slicing a few times, and it's one of the key enabling technologies that's going to allow us to reap the rewards of 5G connectivity. And it allows operators to slice a physical network, including the device, the RAN, the backhaul, and the core network, into multiple end-to-end networks. And we create several virtual networks over a common shared physical infrastructure. So firstly, you've got network function virtualization, NFV, which takes all the physical network resources and abstracts those up into a virtual network layer. And those networks are software defined, which separates the routing and the forwarding to optimize the performance of the network. And orchestration then allows the end-to-end management of each slice. And that allows us to optimize the networks for specific use cases in terms of protocols, quality of service, latency, availability, and security settings. As I say, spectrum is a costly and finite resource, and it will be very expensive or simply impractical to build different physical networks for each separate use case. So network slicing is crucial because it makes investment in physical infrastructure much more commercially viable. It's a paradigm shifting technology because it would be hard to justify the massive global investment in 5G infrastructure without it. Cellular networks today are optimized for the type of data that's processed through your mobile phone. But actually, there are three fairly distinct scenarios we might look to serve through network optimization, and Paul mentioned these earlier. So enhanced mobile broadband, providing higher speeds for applications such as web browsing, streaming, and video conferencing. Ultra reliable and low latency communications, giving reliability for mission critical applications. Industrial automation, new medical applications, and autonomous driving, anything that requires near zero delays in data transmission, and massive machine type communications, which will support a huge number of devices with low individual bandwidth and availability requirements, but with lots of them. So here are some examples. So on the enhanced mobile broadband, you could be looking at ultra high definition video, gaming, extended reality, so that's AR, VR, and MR. In the automotive sector, you're looking at infotainment, and in healthcare, it could be remote surgery. And the emphasis is on the high bandwidth, whereas availability is less important. Ultra reliable, low latency communications. So here we have to have really high availability, and I've got 6 nines on the slide, but there's less emphasis on bandwidth, and there needs to be some emphasis on latency. It needs to be low latency, but it's not as crucial as reliability, I suspect. And this is around it can be used around mission critical IoT and public safety, autonomous vehicles, road safety features, and in the energy sector, communications between power grid substations and the control center, where you need that very reliable, very quick feedback. And then the massive machine type communications. So examples here are sensor grids, telematics and navigation in the automotive sector, smart metering in energy, and in healthcare, non-critical personal health monitors, given that there's a lower emphasis on availability. And by being able to individually service the particular needs of specific industries, telcos could transform from being simply a connectivity provider to being an important business partner for a variety of industries. Business models need to be developed on a per slice or per service basis. So actually these could end up being pretty diverse. It's going to be interesting to see what new business models will be developed to enable those partnerships between telcos and non-telecom players. Thinking for a moment about the legal and regulatory aspects and taking a helicopter view, network slicing is not expected to cause any shifts in the current regulatory regime. The principles and practices of net neutrality, illegal content, quality of service, and cross-border data transfers are not expected to change. Having said that, if network providers are going to shift their business models to take advantage of these opportunities, then it's going to require some organizational change, and they'll need to adapt their approaches. And that means that counsel advising those businesses will be dealing with a different set of legal challenges, or at least contexts, than they may be used to. Privacy and security are also critical, and these can become a little challenging when the slice crosses between spheres of control. If you've got different infrastructures with different security levels and policies, between telecom and non-telecom players, then navigating those differences and making it all work together is going to be challenging. And Paul's going to say a few words about security in just a moment. So how will 5G and AI impact on industrial IoT? Well, no discussion on this topic would be complete without the obligatory diagram showing 4 industrial revolutions. So here it is. Intelligent connectivity is going to drive Industry 4.0, in which robots and computers continually optimize production and maintenance in highly flexible factories and plants. The McKinsey Global Institute concluded that AI and big data are not only contributing to the transformation of society, but as compared to the Industrial Revolution, which is Industry 1.0, this revolution is happening 10 times faster and at 300 times the scale. So that's 3,000 times the impact. The application of 5G to industrial IoT, along with AI, machine vision, and robotics, is going to lead to new operating models that are safer and more efficient. Let's consider efficiency for just a second. So a key indicator of the efficiency of a production line is the amount of time it's not producing anything because it's waiting for something to happen. And that's the cyclic idle time. And the productive portion of each cycle then reflects the efficiency of the line. So this is a really important parameter for those who are operating factories. And manufacturers use heuristic line balancing techniques to determine the allocation of tasks so as to maximize efficiency and minimize their labor costs. And these techniques determine the allocation of tasks based on a pre-specified throughput. But when demand changes, when you need to change your output, you need to reconfigure the line to reflect the new desired flow rate. And with industrial IoT, we can envision reconfigurable production lines that are adaptable to changing requirements. Industry 4.0 will be characterized by self-optimizing production facilities that process a continuous flow of information to automatically adapt to events. These could be supply shortages, signs of a potential machine fault, or even a new customer requirement. And if necessary, you could have specialist machines which could print 3D objects, 3D parts on demand using additive manufacturing techniques, enabling them to repair broken components and reduce costly downtime. Sensors will communicate with motion controllers to enable more dynamic robot motion control. And the addition of intelligence will allow those machines to be more precise and safer for those who are working near them. And we can also expect to see an increase in mobile robots, automatically guided vehicles, and drone technology. So let's have a look at a couple of use cases that might be relevant to a future factory. So the example at the top is the AR head-mounted display. We talked about extended reality earlier, so enhanced mobile broadband seems to fit within that use case. Very high bandwidth requirements, but less so latency and availability. You'd expect it to be non-critical. Handheld terminals and industrial robots. These, you need them to be very available. They need to be working all the time, but bandwidth is less important. You've got a sort of mid-level bandwidth, but latency, you need good latency as well for those to be, because you don't be waiting for your response and things to get delayed. So they feel like ultra reliable, low latency communications use cases. And then process monitoring sensors. There's going to be a lot of these, but individually the bandwidth is going to be very low, and it may be that latency doesn't matter because you don't need that immediate feedback. It's more about just generally monitoring the process and the type of data that manufacturers might want to collect over a period of time. And this feels like it fits within the massive machine-to-machine communications. So it's likely that 5G will help deliver ultra reliable and low latency connectivity to industry through private networks using licensed and unlicensed spectrum, wireless edge computing, time-sensitive networking, and network slicing, allowing specific services to be prioritized. And by capturing information in real time and enabling remote control of machinery, factory-wide connectivity can increase the efficiency of the factory and enhance the value that manufacturers can provide to their customers. So let's think about those enabling technologies for a second. As I mentioned, it's likely that industrial IoT deployments will use a single private network connecting all of the smart components. And this will allow the operator a dedicated, highly optimized and secure network on which to operate. 5G is going to be vital for real-time applications where millisecond and microsecond latency is required, such as extended reality, closed-loop robot control, and automatically guided vehicles. And it will use a combination of licensed and unlicensed spectrum bands. Access to unlicensed bands can be pretty hassle-free, and to the extent licensed bands are needed for the application, it's likely that those will be on the basis of shared or sub-licensed spectrum. Now, depending on the precise application and the particular challenges presented by the environment, it may be appropriate to use LTE alongside 5G, particularly for applications that require lower bandwidth and non-time critical applications where higher latency won't cause a problem, for example, in product tracking and diagnostics. Operators in the UK can currently sublicense LTE spectrum under Ofcom spectrum policy to release unused spectrum and increase industrial usage. And that helps the UK to compete with other countries in deploying industrial spectrum. LTE is also available in Europe, and Germany is pioneering that in particular, as well as the US, which uses the CBRS band. For ultra-reliable low latency connectivity, well, this can be a particular challenge in industrial environments because there are lots of metal objects and that can disrupt the wireless connections. So we can overcome that using a combination of wired connections and coordinated multi-point wireless network architecture. COMP uses a high density of cells with spatial diversity to minimize packet loss arising from the attenuation of signals by obstructions. So in other words, if we take a lot of cells and spread them around, there's always going to be a clear path between the cell and the target. Because the reliability of data transmission has historically been more important than when it arrives, IT networks typically have no concept of time. And under time division multiplexing, for example, packet data is delivered in the next available slot. The Institute of Electrical and Electronics Engineers is developing a set of standards for something that's called time-sensitive networking. And it's largely an extension to the 8021Q standard for the transmission of time-sensitive data over Ethernet networks. And by time-sensitive, what we're talking about is transmissions that require very low latency and very high availability. And these standards focus on giving all the devices that use them a common understanding of time, common rules for processing and forwarding communication packets, and a common model for selecting communication paths and reserving bandwidth and time slots. And they also contemplate using more than one simultaneous path in order to achieve a degree of fault tolerance. This is going to be particularly important for machinery control systems and safety critical mechanisms and autonomous vehicle control, where a failure to get the data through on time could prove fatal to someone. Time-sensitive networking can also be used in industrial IoT to implement other systems that have to react quickly to changes in the environment. So enhancing dynamic precision robot motion control, as well as allowing machines to be time synchronized within the production line in order to improve efficiency. So I think that covers everything I promised to cover in this session. So at this point, I'll hand back to Paul.
Okay, thanks, Chris. So in this last section, we'll just focus on a topic that's caused quite a bit of controversy with 5G, partly, I think, because it involves some quite difficult geopolitical issues. So we can go to the next slide. Yeah, as we discussed earlier, much of the work that supports 5G low latency will take place towards the edge of the network. And given the huge number of devices that are potentially connected, this could present a huge number of potential points of attack for malicious hackers and cyber criminals. And critics of 5G also argue that data on people's location will become much more vulnerable to hackers, and that decentralization of the network will make it much harder to control who gets access to what kinds of data. So the question is, well, how much of this criticism is valid, and how does 5G technology seek to manage these risks? And our own particular view at Fieldfisher is that there are grounds for optimism in the latest 3GPP releases. The security of 5G systems and networks won't be insurmountable. So we can go on to the next slide. So, I mean, you may have heard terms such as false base stations, IMSI catchers, Stingray, and cell site simulators bandied around. In fairly simple terms, they all broadly relate to devices which intentionally set out to impersonate a genuine base station. And release 15 comes with several security features that significantly improve security against false base stations. So, for example, the release contains features that require mutual authentication between devices in the network, so that the network authenticates the device and devices also authenticate the network. So it ought to drastically reduce the ability to impersonate genuine base stations. And in 5G standalone mode, the trust model has evolved, and in essence, trust decreases the further one moves from the core or center of the network, and this has got significant impacts on 5G security design. So in 5G, the base station is logically split. If you look at the flexible framework part of this slide, the base station is logically split into a central unit and a distributed unit, which has got an interface between them. And the centralized unit and the distributed unit can effectively be physically separated depending on the deployment. And provided the operator configures the network appropriately, the distributed unit, which is going to be much closer to the edge of the network, won't have access to any customer communications or data. And so you can see that the further you get towards the edge of the network, the more secure the 5G system ought to be. And in terms of this, so if we can stay on that slide for a second. Cheers, thanks, Chris. In terms of the discussion about the split of the user plane from the signaling plane, just to explain that and unpack it a little, there have always been several security issues in terms of inter-operator interfaces arising from what's called SS7. And that's basically a very traditional signaling protocol that hasn't really changed for about 20 or 30 years. And to counter these sorts of issues around international handover and interconnection of networks, 5G phase 1 attempts to provide inter-operator security from day one. So by splitting the signaling plane of the network from the user plane, that ought to mean that the network functions that are processing user traffic are not actually accessible from international signaling networks. So that ought to decrease the level of risk with things like SS7 and diameter attacks. If we can go to the next slide. So actually, we've been having quite a lot of fun as presenters. Haven't really had to talk about the law at all, but I thought we ought to provide a legislative update in terms of where the telecom security requirements are at. So the supply chain review has probably been going on for about 2 years now, and the first sort of significant publication was by DCMS when Jeremy Wright, I think, was still in charge in July last year. So phase 1 of the TSARS is Ofcom are going to rely on enforcement under the existing regulatory framework. So that's section 105A of the Communications Act, but also reflecting the TSARS in what is currently non-binding guidance and enforcement. And what tends to happen is whenever you have a sort of highly significant network outage, Ofcom will normally investigate the operators involved. So, for example, Telefonica had a big Ofcom investigation where it went down about 12 months, 18 months ago, and also 3 got fined using this existing power of Ofcom. I think they got fined just under £2 million for network security issues. So it's not as if the existing regulatory framework doesn't get used and that this is going to be completely new. But phase 2, which we're probably partway through now, is going to look to embed the TSARS into legislation with a new security obligation requiring operators to comply with the TSARS, strengthening of Ofcom's regulatory powers, and also the creation of new bespoke national security powers for the government to intervene to enforce aspects based on the grounds of national security. So if we can go to the next slide. Perfect. Yeah, so this is in essence a screen grab from July's paper. In essence, it sets out what the level of security sensitivity is based on various different types of network. In essence, anything related to the core network, or authentication and audit, or the OSS parts of the network are seen as being critically sensitive, and we'll sort of see the impact of that as we move the slides forward. So if we can go to the next slide. Yeah, so in January, the National Cybersecurity Centre issued guidance in terms of the TSARS, and this has happened way ahead of any draft legislation, but it was thought that in essence the industry needed clear guidance as they started to roll out or really ramp up their 5G rollout efforts, and also ramped up the delivery of fibre to the premises. And in essence, it highlighted 5 key risks. So the first was basically focusing on best practice in terms of network architecture and software-defined networks and network function virtualization. So there is a series of mitigations in terms of the hardware requirements that CPU manufacturers have got to implement to better protect and separate virtualized workloads. A bunch of software requirements detailing mitigations that hypervisor operating systems and softwares needs to implement. And these mitigations, in essence, focus on helping prevent known exploitation vectors from being available. Then it focuses on the management plane of networks, so segregating critical management functionality from networks with direct access to the internet. And one of the things they focus on in the guidance is that actually, if you go out into the enterprise, quite often you've got an individual working on a workstation that's a corporate laptop that'll be multi-purpose. So actually, that particular workstation may actually be doing some quite sensitive things in terms of management of network endpoints. And so what the TSARs focus on is much tighter control in terms of network traffic permitted between management endpoints and equipment. And it proposes what's called a privileged access workstation. Enables a set of workstations to be, in quotes, known good within the same level of trust as the equipment being managed. And then the signaling systems point I mentioned earlier on, so this separation of the user plane from the signaling plane in networks is again reiterated in the January publication. The last two, I think, have had a significant amount of publicity just because they really focus on geopolitical constraints. So one of the things, one of the 5 risks that the government and the NCSC is trying to manage is a loss of a national capability to operate UK networks. And in essence, what they're saying between the lines is that the UK's telecom sector is very highly dependent on Huawei. So actually, if the Chinese state started to engage in nefarious activities, or maybe continued, depending on your point of view, our ability to literally strip out all of Huawei's kit within operators' existing networks is going to have a significant impact on continuing network availability. And you can see that from the sort of phased announcement that's happened in terms of the amount of market share that Huawei is allowed and which network functions Huawei equipment can be located in. And lastly, and still very significantly, is supply chain risk. So putting obligations on operators to manage the equipment quality and security due to outsourcing of particular activities. So we go to the next slides. So in terms of where we are now in terms of HRVs, this is high-risk vendors. In essence, high-risk vendors should only be used if a bespoke mitigation strategy has been agreed between the high-risk vendor and the NCSC. And in essence, what that means is that ZTE are completely off bounds in terms of the UK telecom sector. And Huawei have had, there's been a facility down in Cheltenham, I think, in terms of the oversight centre for well over a decade. So there is an existing process in place for Huawei, but what has now happened is that their market share has been capped at 35% to limit the UK's national dependency on Huawei. And they will also be excluded from sensitive parts of the network. So that means anything to do with the core, anything to do with OSS, anything to do with authentication, authorization or audit. And there's a whole list in that January network functions for which high-risk vendors are excluded. And so basically the operators have got until the end of January 2023 to actually implement that. And the sting in the tail is because of the entity listing in the States, even that decision to limit Huawei to 35% and to keep them away from sensitive parts of the network is currently under review because of the US entity listing. So expect further developments in that as over the next month or so. And lastly, keeping high-risk vendors away from sensitive locations. So anything close to a location that has got a particular national security facility and away from sensitive networks as well. So, I mean, due to time, I've not gone into this in a huge amount of detail, but we've actually written a paper in terms of cybersecurity and 5G. So if you'd like a copy of that, then just drop me an email and I'll send it to you after the talk. So that was all I wanted to cover. Have we got any questions from the floor?
Yeah, so if you've got any questions, please do use the questions tab and send those through. The first one we've got, I think, for Chris. Do you think 5G will be important in adapting to life post COVID-19?
Yeah, that's an interesting one. When I was talking about the various use cases earlier, I touched on wellness as being one of them, and I was tempted to reference the pandemic, but I know that everyone's hearing a lot about it all the time, so I didn't want to add to that. But I think the answer depends a lot on what timescale we're talking about. So in the very near term, I think no, I don't think 5G is going to get rolled out in order to combat the current crisis. But I think in the longer term, I'd probably say yes, absolutely. 5G could support technology in buildings to make them healthier and safer. So you can have scanners and air purifiers and so on. It could support wearables, so thinking about track and trace, as well as providing. I mentioned, critical and I mentioned non-critical health monitoring. You could extend it to critical as well within healthcare environments. And of course, it could really help us to work from wherever we happen to be from time to time, rather than having to congregate in one place. So remote working, there's benefits there. So I think there's all kinds of ways in which 5G could be important in the longer term. Yeah.
Thanks. And then another one for Paul. You both expressed doubts that 5G will be a silver bullet. What other communications technologies will help to get us to this vision of the future?
Yeah, I mean that's a good one. I think the investment business case is going to be critical, because last few months won't have helped anyone's balance sheet. And I think the question is, for me anyway, is there is always going to be a trade-off between bandwidth requirements, speed, and cost in terms of network solutions. So I wonder, with some of the very low data rate applications, I can see that a 5G solution may not be required. You may just need either a 4G narrowband IoT, or potentially implementing something like LoRa or Sigfox or weightless, one of those alternative technology solutions that may be cheaper, where if you're not actually communicating vast data streams, and existing technology may suit you. And certainly we can see that in terms of some of the tracking devices that clients are implementing right now.
Thanks. I think that's all that's come through on the question side, but if I have missed anyone, please do email, and conscious that it's just after 3.
Great. Okay, thanks all.
Thanks, everybody.